Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at a question that Andy Robertshaw asked about hyperbolae and the parametric definition. The hyperbolae look interesting. Is y equals 1 over x occupying the first and third quadrants, a rotation of x equals a sec t, y equals b tan t, where that's the parametric definition of the hyperbola. So let's have a look at this. Let's get to know x equals a sec y, or that should be a t there, look, shouldn't it? Oh, we can correct this in real time. We can do this. X equals a sec t, y equals b tan t. So we know this, sine squared plus cos squared equals 1. This much we know. Divide everything by cos squared. That tells us that tan squared t plus 1 equals sec squared. And then if we swap sides and we take tan squared away from both sides, it says that sec squared t minus tan squared t equals 1. Or, if we do some rearrangement up above, sec squared t is x over a squared, and tan squared t is y over b squared. So it says x over a squared minus y over b squared equals 1, which is the standard presentation of a hyperbola. So that just shows that the parametric expression is the same as the Cartesian one. Now this is what x squared minus y squared equals 1 looks like. So it's these dots, beautiful hyperbola, and these are the asymptotes, y equals x, y equals minus x. So in the limit, basically as x goes to infinity, x and y become virtually equal because the 1 becomes irrelevant, so x squared just becomes close to y squared. So when y equals 0, then x is 1. So they're very different. But when x is a really big number, then y is almost the same number, because essentially x squared equals 1 plus y squared, and the 1 becomes irrelevant. And then this is the more general case. This is x over a squared minus y over b squared equals 1. And here the asymptotes are y equals b over ax and y equals minus b over ax. I mean, just to check that, if you put in b over ax in for y here, the b's cancel and you get x over a squared, which in the limit is true because the 1 becomes negligible. Okay, so what we're going to do is we're going to sort all this out by taking a vector approach. Now this diagram is going to become helpful, but let's just explain. Firstly, we're going to write the parametric expression of the hyperbola as a vector. So xy equals a sec t, b tan t. And then what we're going to do is we're going to put together a matrix which corresponds to a rotation of 45 degrees anti-clockwise. So this x is going to go to x prime, which is 1 over root 2, 1 over root 2. Those are the two coordinates. This is the new x-axis in a sense. And then this y is going to go to y prime, which is the x coordinate is minus 1 over root 2 because it's negative. And the y coordinate is 1 over root 2. And the reason they're all 1 over root 2 is because this is 1. And then by Pythagoras, these are going to be 1 over root 2. So you square it, you get a half, plus a half is 1. That's what's going on. Okay, so these are the two transformed versions of the axes, and so then that helps you build a matrix, which is 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. And then we're going to multiply this parametric expression of the curve by the matrix. We're going to transform it using the matrix. I know it sounds like a well-known movie, but the mathematics came first. Anyway, so if you multiply this matrix by this lot, what you get is you get a sec t minus, I mean, you take 1 over root 2 out because 1 over root 2 is everywhere. So this is just 1 minus 1, 1, 1. A sec t minus b tan t is on the top because you multiply that by that and then that by that. Then on the bottom you've got a sec t plus b tan t, which is this thing. You've got 1 over root 2 as a factor for all of it. So what we got then is, this is the kind of parametric expression of the rotated curve. X equals 1 over root 2 a sec t minus b tan t, and then y equals another similar expression. So what we're going to do now in a stroke of genius is we're going to multiply these two together. So 1 over root 2 times 1 over root 2 is a half. And then here you've got a sort of difference of two squares thing. So this times this is going to give us a squared sec squared t. This should be here. Sec squared t minus b squared tan squared t. That's what xy equals. So here it is. We'll put this squared in. So if we were to set a equal to root 2 and b equal to root 2, then this a squared and b squared would just become 2. And then 2 over 2 just cancels away. And then you get sec squared minus tan squared. As we showed earlier, that's just 1. So magically, this comes out to xy equals 1, or y equals 1 over x. So basically, the answer to Andy's question is yes. And the short answer is yes, 1 over x is a rotation of y, x equals a sec t, y equals b tan t, as long as a and b are 1 over root 2. Hang on, let me check they're 1 over root 2. Or are they just root 2? As long as a and b are root 2. If a and b are root 2, then the answer is yes. But, I mean, to be precise, which we need to be because we're mathematicians, this expression is slightly more general form of the hyperbola because, of course, you can a and b are parameters that you can alter. So this is a slightly more sort of general expression, but this lower thing, the parametric expression, does rotate onto y equals 1 over x in the case when a equals root 2 and b equals root 2. I hope you liked the video. I liked it a lot. Please hit the like button. Please subscribe and hit the notification bell. I'd love to hear your ideas. You know, Andy contributes a lot. Other people contribute. It's a good thing because, you know, if we all sort of develop and discuss the ideas, everything gets better. Nobody's perfect, but we work together and we get to the truth. That is the collaborative journey of mathematics, and I hope you enjoy it. See you soon.